Hello, and welcome to a tutorial lecture on torsion for ME 501. This is the introduction slide, and it shows some kind of interesting things that we'll talk a lot more about later in this section. First of all, we see that for certain materials such as wood, torsional failures can be very fast and not a lot of time given before the torsional failure actually occurs. Down here we see that in pure torsion we have an I-beam, and these are the stress profiles in the sections of the I-beam. We also see this term called warping, and we see an I-beam here that has shear stresses in the flanges and normal stresses in those flanges. And we'll talk a lot about warping and how these shear and normal stresses are developed and computed. Here we can see in this I-beam that under torsion we get this end to go up quite a bit, this end going down, and then we see that we get a shift in the geometry. And we're going to want to be able to compute this angle of rotation, theta. This is a very interesting picture. We see that we had a square beam, and this square beam was subjected to a torsional load. And note where the maximum stresses occur. Here in the corners of the square cross section, the torsional stress is very small. But in the straight long sections, and more specifically right in the middle of the long sides of the square cross section, the shear stresses are the largest, which certainly could be counterintuitive. Down here we see that there are many applications of torsional loads and how they can, in this case, use a torsional spring that twists up as you lift up the door and helps carry some of the load so that your garage door is much easier to lift up and then does not come down super fast and just slam down, but it comes down slow as well. Kind of interesting in this slide, if we look at this first picture here, we can see that this line represents the unloaded state, and we see that we have a nice rectangular element. Then as we twist this beam and we get some deflection in the beam, this rectangular element has now shifted and looks more like a diamond shape. And it's important to remember that that change in right angle in going from this element to this element is the definition of shear strain. So shear strain is that change in right angle. Note here's a typical failure of a member in torsion. You can see that that failure looks a lot different than like a brittle fracture failure, where you would have more of a straight cut through the member if you had a tensile load. So it's kind of important that we're able to distinguish torsional failures versus normal stress failures based on the way the failed specimen looks. This diagram here is kind of showing us how the stresses occur in an element. Here we have the unloaded specimen, and we just have no load on this little stress element here. Then as we twist this element, we can see that it develops shear stresses along these faces. And once we have shear stress on these faces, in order to keep the member in equilibrium, we also get shear going along these other faces. This is the idea of warping again. Here's an I-beam, and what warping really is it's this extension and this reduction in the cross section that occurs when the beam undergoes torsional loading. Here in a circular cross section, we see that these planes all remain perpendicular um, to the axis of the cylinder. But over here in a square beam, these planes now have changed and they are no longer perpendicular to the axis of the beam. And so that's what can introduce this warping effect, where warping again is the extension in the axial direction due to a twist. Torsion problems are awfully categorized into three different sections. The first section is just solid cross sections. And in these, we use the St. Venant's torsion theory, and we will go over that in this lecture. The other class, or one of the other classes, is what we call open thin-walled sections. And you can see that these are sections that are made out of thin-walled material, and they're not closed. The closed sections for thin walls are the third category, and you can see here that this circular tube would be a closed section. In the open section, we use a membrane analogy, and what we do is we look at a soap film on top of this end of the cross section, and we'll talk about that. And then in the closed thin-walled section, we use Brett's formula. Here are just a few equations that might be helpful to you. The relationship between power and torque and angular velocity. And then we can look at horsepower conversions. This next slide starts to go over the development of the TC over J equation that we have for circular members. As I will not expect you to be able to derive the equation TC over J, I'm just going to go over a brief overview of the development. What we start with is a circular rod, and in the undeformed state, this line would be a straight line from A to B. Point D is just another point that is closer into the center of the shaft. Then we apply a torque, and point B rotates to B prime, and D rotates to D prime. Now if we look at the end of this and blow it up a little bit, this is what we would see. We would have the angle theta in the rotation from the center of the cross section around to the deformed geometry. That angle would be theta. And we note that the angle from D to D prime is the same as the angle from B to B prime. So that's theta. Gamma is this angle here. If we take the AB line and draw it as this horizontal line, and then if we approximate the AB prime line as a straight line, we get this triangle that represents this up here. And the angle back here is gamma. And so we have two angles. We have the angle gamma and we have the angle theta. Now for equilibrium considerations, we sum the moments, and the summation of moments results in the applied torque minus the integral from 0 to rho, which is from 0 to the outside radius of tau rho dA. Note that tau would be the shear stress, and the shear stress times an area would be a force, and then a force times the distance rho is a moment or a torque. And so that's why the torque minus this component equals 0. If we look at the assumptions that we're going to make, we're going to assume that the element analyzed is distant from the applied loads and external constraints. And this is one thing you're going to have to watch for if you try to compare FEA results with hand calculation results. You need to have long beams that are in torsion so that the applied load is not very close to where you're trying to compute the stress. And then your answers will compare well. But if your torque is too close to where you're trying to also compute the stress, the FEA results and the hand calculation results will not compare very well. We're going to assume that the bar is subject to pure torsion in a plane normal to its axis and no other loads are applied, so we're getting a perfect pure twist here. We're going to assume that cross sections of the bar remain plane and perpendicular to the axis. So we're going to be looking at cases like this case here where the planes remain plane and perpendicular. We'll look at this case here a little later. We're going to assume that adjacent cross sections originally plane and parallel remain plane and parallel, and that radial lines remain straight. And this does not hold true for the non-circular cross sections that we will eventually look at. What we do then is we take the tangent of gamma, and you can see here that the tangent of gamma is the opposite over the adjacent, so we could say the opposite side was DD prime, and the adjacent side was AB. And so here we have DD prime over AD, and we can write DD prime as rho d theta using the arc length equation. So this DD prime would be the arc length for rho and theta. Then for small angles, we're going to assume that the tan of gamma equals gamma. And this is different than MC over I. We don't make the small angle or small displacement assumption in MC over I. But here in TC over J, we do have a small angle assumption. And then we can come here and we can say that the gamma C equals C theta over L and gamma D equals rho theta over L. And those are just the various arc length equations again, replacing these with specific locations for C and D. And we know that the theta here has to equal the theta here, so we can solve for theta in this equation and this equation and set those two equal to each other. And when we do that, we can find out that gamma D is proportional to gamma C by the ratio of the radii. Then we'll come back and use Hooke's law. So this is assuming an isotropic, homogeneous, one-dimensional situation. We'll multiply both sides of this Hooke's law by G, and when we do that, we get G gamma D, G rho gamma C over C, and this we can write as TD, and here we have a tau D, here we have a tau C, and we can see that these two shear stresses are related by, again, the ratio of the radii. If we come back to our equilibrium equation now and substitute in expressions for tau that we have up here, we can see that the torque is equal to the integral from 0 to rho of tau, rho squared over C dA. And this integral of rho squared dA is what turns out to be J, or the polar moment of inertia. And so that leads us down here to T is equal to tau J over C, or tau is equal to TC over J. And we can solve for theta and get these expressions here. So that's just a quick overview of the tau equals Tc over J equation for solid circular members. And it's important for you to remember and realize that tau equals Tc over J is only good for circular cross sections. It does not work for any other cross sections. This here is a really handy table for different cross sections that occur, and you can find tables like this in many textbooks and online material. In this case, for example, we have a solid square. The expression for K is given here by 2.25 a to the fourth, where a is half of the length of one side, and Q is given by a cubed over 0.6. And then we take this Q and this K and we plug them in to these equations up here, and we can compute the stress and the angle of twist. It's kind of nice. This table here also shows us where this stress is being calculated. So these equations here represent the shear stress at these dots here. And it happens to be that these dots represent the highest shear stress state in that particular cross section. And again, we note that the highest shear stresses occur in the middle of the longest side of the cross section. Here's an example that shows us the importance that adding material to the outside of the shaft or the outside of the cylinder can have in terms of torsion. So here it says, after designing the structural torsion member shown in the figure. So this is what was our initial design. Mechanical engineer discovered the design torque had to be increased, and the engineer decided to redesign the member by welding a structural steel sleeve with an inner diameter of 80 and an outer diameter of 86 to the member as shown in figure B. So originally this inside core is 50 millimeter diameter and these outside cores are 80. And then in a retrofit, the inside core here was 80 and we extended that with out to an 86 millimeter diameter. So we added this sleeve to this rod here, and what we want to determine is the design torque for each of the members in the two figures, and then we want to calculate the increase in torque resulting from the sleeve, and we will compute the increase in the weight and compare that and see if the additional weight was worth the gain in stress. So to do that, we have to get the polar moments of inertia for the different sections. So here's the polar moment of inertia from O to M, and here's the polar moment, here's the polar moment of inertia from O to E. And you can see that these are just the different diameters. Here's the 50 millimeter diameter, here's the 80 millimeter diameter. And then the torques in the middle and the end sections then would be given by tau J over R. And here's the radius, here's the J, the associated J, and then the applied torque. And so we can see that the maximum shear stress that would be allowed. And then here we get the applied torque. So we can see that since the TOM is a lot less than the TOE, the design torque is for the TOM section. And we could have guessed that. Coming back to here, we know that this thin member here will not take as much torsional shear stress as these much larger members on the outside. So this just confirms what we already know, and we have our baseline calculations to compare to. Now we want to look at the polar moment of inertia for the modified member. If we do that, the JMM, so this is the modified member, would be the original insert, the JOM, for the 50 millimeter diameter. And then we add this outside tube, and that's given by the outer radius of 0.086 meters minus the inside radius of the tube of 0.08, which gives us a 1.9 e to the 6 meters to the 4th JMM for the modified member. The other J's for the rods where there was no change, that stays the same as what was computed up here before. Now we compute the torques, and just like we did in this section, and we see that the torque for the modified member is 2.7 kilonewton meters, where up here we had 1.473 kilonewton meters. So we can see that this torque for the modified member has increased significantly. The design torque with the modified design then is 2.738 kilonewton meters. And if we look at the increase in the torque, we had an increase of 1.265. If we look at a percent increase, that was an 85.8% increase in the amount of torque that that shaft could take. And if we look at the weight gain, here we can compute the volumes and then we multiply by the specific weight. It ends up that the volume change was 9.3%. So we had a gain of 85.8% in the amount of torque that shaft could take, and we only had a 9.3% gain in the weight. So the illustration here is that if you need to increase the torque carrying capability of the shaft, the best thing to do is add material as far away from the center of the shaft as you can. And that really helps increase your eyes, your moments of inertia, which then really lets you increase the stress in that member or increase the torque to get the same stress in that member. The method that we're going to use to look at the stresses in solid members with non-circular cross-sections is based on St. Venant's theory. It's also called the semi-inverse method, and this is talked about in your textbook in section 6.2. So the words and data and examples and stuff parallel that section 6.2 very well. So the development of the torsion equation on the previous pages, the TC over J, as we know, is only good for circular cross sections. And there are other methods to compute the shear stresses in non-circular cross sections, and one of these is the St. Venant's theory on torsion. There's actually several models. Some of these include the warping function model, the conjugate harmonic function model, and then St. Venant's. But of these, by far, St. Venant's stress function model is the most popular and most commonly used. The drawbacks to this, or the challenges, become in that this is a semi-inverse method. And if you recall that for semi-inverse method, it consists of specifying part of the displacement or stress field, and then using the boundary conditions and integration of the other field equations to determine expressions for the stresses, strains, and displacements. And so we have kind of a hybrid method here. The assumptions in St. Venant's are that the cross sections are free to warp in the z direction, but that the warping is the same. So what this means is that as you twist this beam, it's actually going to extend in the axial direction, and that extension is the same all along the length of the beam. The second one is that cross sections do not distort in plane during twisting. So every point in the section rotates through an angle about the center of twist. So the part will have a constant center of twist, and if you move out in a radial direction and then twist, all of those elements at that radial point will rotate through the same plane. There are no rigid body displacements or rotations. The rate of twist is also assumed to be constant along the z-axis, so you don't have more twist along the length of the beam, but it's assumed to be all constant. And so our cross section is essentially constant along the length of the beam. The development of the St. Bernard approach starts by looking at the displacements in an arbitrary cross section. And once we get an expression for those displacements, we're going to use the strain displacement equations to get the strains. And there are compatibility equations that help us solve these strain displacement equations so that we can extract the strains from the displacements. Then we will use equilibrium equations, and equilibrium equations let us use the strains to compute the stresses. And we'll use Hooke's law in that process of using equilibrium and Hooke's law to take the strains and compute the stresses. So it sounds like a lot of work, but this is kind of the common approach. We'll get expressions for the displacements, use those displacements to compute the strains, and then use those strains to compute the stresses. So if we look at the cross section of an arbitrarily shaped beam, when St. Bernard did this, he defined the vertical axis as the x-axis and the y-axis as horizontal to the left. So we will use this x and this y-axis, and the hardest thing is trying to remember that to keep things straight. Now when we use the x-axis, we talk about any displacements in that direction as being u displacements. When we look at the y-axis, we talk about any displacements along the y-axis as being v. So what we have here is we had a point P in the undeformed state, and it was at an angle alpha from the x-axis. We then applied the torque, and P moved to P prime, and it rotated an angle beta. And P and P prime are both at the same radial distance from the center, R. Now what we're going to do is this arc length between P and P prime would be given by R beta. We're going to assume that R beta is a straight line. And we're going to break R beta into its x and y components. So the vertical component here we're going to call u because that's the displacement in the x direction. The horizontal displacement we're going to call v because that's the displacement in the y direction. Note that this alpha in here is the same as this alpha here. And now what we want to do is develop expressions for u and v. These expressions for u and v are given on the next slide. We see that u is equal to the x prime minus the x. And we can use these equations here to express that. We can see that this would be the x prime would be r times the cosine of beta plus alpha, and then x would be u times the cosine of alpha. So if we subtract that, this is the equation we would get for the displacement v. We get the same thing except we have the sine of those angles. Using trig identities, we know that the cosine of beta plus alpha can be extended into this expression. Sine can be extended here. And so now if we assume small beta, these angles become the cosine of beta plus alpha is the cosine of alpha minus beta sine alpha, and similar drop-offs here. So we know that if we have small angles, the sine of that angle becomes small and essentially is that angle. So the sine of beta simply becomes beta, and the cosine of beta becomes 1. So here the cosine of beta would be 1, leaves us cosine of alpha. Here sine of beta becomes just beta, and we have the sine of alpha, and so on. So now if we take these and substitute them into those expressions, this is what we get for u and v. We remember that r is x squared plus y squared, and so substituting these in, we can come down and write expressions for u and v in terms of theta as minus theta zy and theta zx for v. And these expressions will be really handy for us. Now what we're going to do is we're going to let w equal theta phi, where this phi is the warping function, and you note that it's independent of z. It's not a function of the length of the beam. It's important to note here that w is the displacement in the z direction. So this is displacement along the length of the beam, and this will be like our warping function. And W will represent a measure of the warping, where phi is the warping function, and then theta is our twist. So for small displacements, the definitions of the strains are given by these equations here, where the strain in the x is simply the change in the displacement, or the displacement in x, the derivative of the displacement in x with respect to x. This would be like change in length over length. And these are the definitions for all the normal strains and then our shear strains. And now to get to the geometric conditions or the compatibility equations, we substitute the displacements into the strain displacement equations. So from equation number 1 on this previous page, from these equations right here, we have our displacements, and rewrite them here. And now our strain displacement equations are given here. These are called again strain displacements because they have the strains and the displacements in them. So we're going to substitute these displacements into these strain displacement equations and compute the strains. And note that there's no change in u along the x, no change in v along the y, and no change here. So u and v are actual, they would be like a number, but the derivative or the change, there isn't anything. And because we assume the cross section doesn't change shape, we get that the shear strains must be 0 as well. And so our shear strain gamma xy is equal to 0. But now we need to be careful because these other shear strains, the gamma xz and the gamma yz, those are not 0. And so when we substitute these in, we end up getting these expressions here. And we don't know this phi term. We don't know what the warping function is, so we want to try to get rid of it. And we're going to use these two equations to get rid of the phi here. So we're going to take the derivative of gamma with respect to y, and the derivative of gamma yz with respect to x, and we get these two expressions. And now, if we're going to subtract these two expressions. And when we do that, note that this second derivative of phi with respect to xy drops off, because we would have the partial of gamma xz with respect to y minus partial of gamma yz with respect to x. And so we'd have this theta term here that would then have this term subtracted from it, and those two terms would drop out. And that leaves us with this expression here. And this is what we call the geometric compatibility equation. And we'll come back to this when we talk about equilibrium. The next step of what we're going to do is we're going to compute the stresses based on the strains that we have. So we're going to assume Hooke's law for isotropic materials. These are equations 232 on page 87 in your textbook. And you're familiar with these. You've seen these before. We talked about these in 372. So here's the modulus of elasticity. And you got to be careful. This V down here is actually nu, and that's Poisson's ratio. And so what we have with the Hooke's law equations is we have the stresses related to the strains. And note that if we had just one-dimensional strain, then these strains would drop off, and we'd have 1 minus nu, and this would end up looking like sigma equals EE if we had an isotropic one-dimensional material. So this is just letting us have three-dimensional materials. We know that in torsion then that the sigma YY and sigma ZZ and sigma XY equals 0. So those are zeros. The only terms that are not are the ZX or XZ and the YZ. And these stresses are not 0. So we have expressions for all the stresses, and now we can take and substitute these into the equilibrium equations. And when we do this, we're going to assume that all the body forces, such as gravity or magnetic field or something, are 0. And then the equilibrium equations listed here on page 240, or equations 245, page 51 in your textbook, reduce to this set of equilibrium equations here. And to make the third equilibrium equation valid, we know that our stress function phi must satisfy these conditions. And now what we do is we look for a function phi that will satisfy these conditions. The third equilibrium equation becomes this when we expand it out and insert this definition of stress into the equilibrium equation. So this is now my equilibrium equation. And this phi again is called the Prandtl stress function. And the goal is to determine phi that will allow us to solve the torsion problems. Note that in the following approach cannot be used for anisotropic materials because you can't separate the shears from the normals. But in orthotropic materials, we can. And where that comes into play is back here in Hooke's law. So if you have shearing strains related to the normal stresses, then we can't use this St. Venant's approach. So you'll note that these shear stresses are independent of normal strains and normal components. In order to determine this phi here, we need to consider what the boundary conditions are, and that'll help us determine phi. If we look at the boundary conditions, here's my cross section, and I'm going to take a little stress element right here. Note that my coordinate system is now x in this direction and y vertically. So this stress coming out of this would be the stress in the z direction on the x face, and here we would have stress in the z direction on the y face. If I come down here to a little element on this edge, what I know is this would have a normal component. The normal to this little stress element, to this little curved section right here, the normal to that geometry is this normal n. And what we're going to do is take this and kind of blow it up. We know that the normal stress component is 0. Everything's torsion. So the torsional stress is going in this direction, and it would have a zy and a zx component. And we can compute what those are based off of these two expressions here. And we can also define alpha as dx ds, or the sine of alpha is dx ds, and the cosine of alpha is dy ds. So the component of the shear stress tau on the surface in the normal direction is 0. So this normal component is 0. And we note that the shear components of stress are tit to tail, as we talked about here. And so using that, and the idea that the component of tau in the normal direction is 0, we can take the projections of sigma zx and sigma zy in the normal direction, and they must sum to 0. So sigma zx projected in the normal is sigma zx cos alpha, and sigma zy is sigma zy sine alpha. So we can see that by these projections into the normal direction, or into this direction here. And we get these terms, so we know that this has to equal 0. Rearranging terms here and substituting in, we get this expression. And then we recall the definitions of the stresses, so we can put these phi terms back up in here for the stresses. And substituting this in, we get this expression right here. And so we can see that phi must be constant on the boundary for this to happen. And so we're going to take this derivative, and the derivative will be 0 if phi is a constant. So phi equals 0 on the boundaries, we're going to let it equal that. And when we do that and come over here and sum forces, we get the summation in x, y, and the moment is given by this equation right here. And now as we continue to do the x forces and the moments, we get some kind of nasty integrals. We have to integrate this one by parts. But the end result is that we get the summation of the moments is equal to the torque times 2 times the integral of phi dx dy. And this phi is the stress function that represents a surface that exists over the cross section. So this phi right here, it can be like a bubble. Phi is a function that represents a bubble on the end of the cross section of the member. And then based on the boundary conditions, and like a bubble, the stress function is 0 on the boundary. So what you want to do is look at your boundary, look at a cross section, and pretend like that's a full of soap film. So this would be the perimeter, and then this is full of a soap film, and you just blow into it to make a bubble. And as it bubbles, the shape of that is given by phi. That's this phi here. And we know that the boundary condition is that that has to be 0 on the boundary. And this relates this to the torque. So from the summation of moments equation, we can see that the torque is equal to twice the volume between the stress function, or the bubble, and the plane of the cross section. So as we continue to build on that, all the equations up to this point are the same for orthotropic materials, but now we're going to require linear elastic isotropic materials. and given by equation 5, this is the definition of our stresses. And we're going to substitute these into these simpler Hooke law equations, and we get this here. G is the modulus of rigidity, and using the same procedure for x, y, using the same procedure for zx as zy, we get this for zy. And so now we can come down here on our strain compatibility equations and get this expression. And when we substitute the expression of these stresses in terms of phi from equation 10 up above, we get these expressions for gamma xy and gamma zy. And we can go back to the geometric compatibility and we get this expression right here. And this is known as Poisson's equation. The phi here is the angle of twist per unit length. And now we can solve for phi because we know it's equal to 0 on the boundary. And one thing that's important to note is that once phi is determined, the expressions for the stresses and the torques can be determined. The solution to phi is not easy, and so what we do is we look at an indirect approach for doing this. And for orthotropic materials, there's not a common shear modulus. So for orthotropic materials, you get this harder equation, but you can still use it to make things work out. So let's just take a summary of St. Venant's theory on torsion. First of all, we solved the Poisson's equation below, subjected to the boundary conditions, and then that gets us phi. Then we get the expression for the torque by integrating phi, and this equation is used to determine the J-like terms for the cross section. So in the equation TC over J, we can't use J, but we can solve for a J-like term using this equation right here. Then we can come back and compute the stresses because we know the stresses are defined in terms of phi like this. And the resultant shear stress is given by the square root of the sum of the squares of the stresses. Then from the stress equations and the definitions of the strains, we can get W from these equations, and W is our warping function. And then we get U and V from equations 1, and then we can compute the strains from the stress-strain relationships. And then after that, we get this second order partial differential equation, and we're going to let the boundary of that cross section be defined by the function f. And if we let the boundary or the perimeter of that cross section be given by f, we're going to assume that phi is equal to some b, where b is a constant times the perimeter or boundary equation. And so substituting that into this expression, we get this equation here. Now this equation we can solve because this f is simply the equation for the perimeter, and we can know what that is because we know our cross section. So this is a big simplification that lets us solve for phi by assuming phi or letting phi be a constant times the perimeter. This probably sounds a little confusing right now, but we'll go through some examples that make this much easier for us to understand. This page here just simply shows the boundary or perimeter equations for a few common geometries. For example, the circle here is given by x squared plus y squared equals r squared. And we know that for an ellipse, we have this equation for f. For an equilateral triangle, this can be shown. And for a rectangular cross section, we can get phi as given by this equation. And note that this is phi here. This is not f for the rectangular cross section. So if we want to determine b, which will let us determine the phi and equations for the stress for circular cross-section. This is how we would go about doing that. We know that our boundary condition equation is x squared plus y squared equals r squared. That's the equation for the perimeter of the circle. And now if we put this in the form for phi, this is simply b times this function f. And now we take the derivative of phi, and we have to take the second derivative. So if we take the second derivative of phi with respect to x, we'd get 2x, and then just the x would drop off and would end up with 2b. Same thing for the derivative with respect to y twice. So putting these together, we get 2b plus 2b equals minus 2g theta. And solving for b, we get minus g theta over 2. And this expression satisfies the compatibility equation exactly. So the equation for torsion, derived using this boundary function, St. Venant's approach, is exact. Then what we can do is come over, and our phi is given by this. So we're going to substitute this phi into this equation for t, and to determine the expression for the torque. And when we do that, we get this integral that we have to integrate. So we've got the torque times this x squared plus y squared minus r squared. Our minus g theta is our b term. These are our integration limits for a circle, and this is kind of a nasty integral, but as we go through that integral, we can solve for the torque. And when we get down here to the expression for the torque, and we're done with this, we can see that the torque is g theta, and then we end up getting a 4/3, 1/4, 3/2 r to the 4th pi. And rearranging this, we get g theta pi r 4 over 2, and we can recall that theta is the partial beta with respect to z, where beta is the amount of twist. So taking the derivative of this, we can substitute this in, and we can show then that j is equal to pi r to the 4th over 2, and that's exactly what we get for a circle. We know that I usually use the expression j equals pi d to the 4th over 32, and that's what you'd get here if you were to change r to d. So now we can look at the stress components, and this would be the definition of zx and zy in terms of the partials. And we get these two equations. We take the square root of the sum of the squares, and we can see that we get that tau is equal to tr, or tc, over j. And we know that that's exactly the definition of the shear stress that we got and used before. So you can see that St. Venant's approach is a little bit messy. These integrals can be tough, but if you know the boundary of your cross section, you can do the math and get the integrals and come up with the expressions for the torques and then the stresses. If I have you do this, I would have you do it for a simple geometry. I'm not going to expect you to be able to do an integral like this on an exam, but I would expect you to be able to know the process and St. Venant's process for doing a problem like this. We'll stop here and continue this on Monday of next week.